Okay, so we're going to evaluate Thevenin analysis by using an example with a resistor load and a circuit that feeds that load. So let's build the circuit together. As you can see, we have a power supply, voltage power supply. There will be a couple current sources for this, and I'll label accordingly where the resistance load is between A and B. We're going to give it a value. Now this would be the circuit that feeds the load. So it has its own network. As I said before, two current sources, and a voltage supply. Okay, so again, as a reminder, we are interested in the Thevenin analysis for this circuit. And the point of that is to find an equivalent circuit that has an equivalent resistance, internal resistance, an equivalent source of voltage, right? So it will supply power over to the load. So the RTH and ATH are your equivalent circuit between A and B vis-a-vis the load. So as far as the load is concerned, what it will see is an equivalent voltage supply and an equivalent resistance. So we need to find these items. So we will start with the equivalent internal resistance RTH. To do that, at any time you're doing Thevenin, we will remove the load, so the circuit between A and B, or the link between A and B, is open. Next, we will short all voltage supplies and open all current generators or supplies. So this is an equivalent circuit of what I just stated by shorting the voltage supply and opening the current supplies. What we end up observing between A and B, we have two resistors in series as seen through A and B. So RTH will be R1 plus R2. Okay, so it's all relative to A and B. In our case, it's going to be 20 plus 30. Which is 50 ohms. However, the problem really started out with 10 ohm for R1, so let's change that. So now that changes our total now to 40 ohm. Okay, now that we have RTH, let's go ahead and look at ETH. And this is going to be done in several parts. So we're going to look at each part with one single generator at a time. Okay, so we will start with the voltage supply in place, but the current supplies will be open. And again, between A and B, it should be open, no load. Okay, to further illustrate this, as you can see, these are virtually where the current supplies would have been. And we're leaving those open. So we're interested in ETH-A at this stage, since this will be stage A. Okay. Now remember, E is pointing down. But the thing about this is that the circuit is open. There is no path. There is no complete path for any current to flow through this. So the only voltage we see at this stage is E. However, vis-a-vis VAB, it will be minus E. If we use a reference of VAB, that is. So ETH-A is minus E. Okay, so the next stage, what we will do is short the voltage supply, put one of the current sources in place, and leave the other one open. Again, A and B with no load. So this will give us ETH-B, which is partial ETH. Okay, and we're illustrating here that the other current supply at this stage is still open. Okay, so we're only going to utilize the 2 amp current supply. So we're interested in ETH-B, which is really VAB-B at this stage. And so we have a current, 2 amp, going through R1 and R2. That is the same current going through that loop. And we have voltage drops opposite to the current. Which leads us to minus, actually, 2 amp times R1 plus R2. Since we're always looking vis-a-vis VAB. Okay, just filling in the values for A and B parts. Now, part C, we will put back the 1 amp current generator. We will leave the 2 amp open this time, no load, and we will short the voltage supply. And again, the idea is each step you will only handle one form of power supply, either be it current or voltage, at a time. Notice now we have a complete loop between the 1 amp generator and R2. The circuit through R1 is open, so there is no current through R1. So A technically can be below R2 in terms of measuring voltage between A and B. So vis-a-vis VAB, and again, the voltage is opposite, so this will be a negative value. Excellent. So at this stage, we will be interested in the total ETH, which would be the sum of the partial ETH. So now we will evaluate again for correctness. Before I add these up, we would like to make sure that the signs are correct and everything was done vis-a-vis VAB. Always double check before you take a final decision. Okay, very good. So now we add them, but we're going to have to put a minus in front of 170 because the power supply relay is pointing the other way. So at this stage, if you want to keep it this way, it will be a minus 170. Otherwise, you're going to have to redraw the circuit with the power supply flipped the other way. So let's do that. This time positive 170. However, remember, I'm interested in VAB and IL at this stage. So the current load and the voltage against the resistor. So VAB, as you can see, will be a negative value, since voltage will always be opposite to the current. At this stage, let's assume IL is positive relative to its power supply. So that is the way we're going to calculate this. However, we have to be really careful with VAB and make sure that you assign it a negative value. So again, applying Ohm's law. Total current equal total voltage divided by total resistance in a series circuit. And this would give us a 2.833 amp or amps. This is an approximation. Now, VAB. Make sure you put a minus sign. Otherwise, if you did VBA, then you can leave it as a positive value. And once this is calculated, it will be approximately minus 56.6 volt. Don't forget the minus sign.